Good morning to all. Today we are here to present our project on the topic Elderly Fall Detection System using mmWave radar sensor. I am Amalda Tereshon and my teammates are Arthakrishna S. Nair, Jeslet Joy and Angel and Alex. We are guided by Assistant Professor Srish P.R. These are the contents included in our presentation. Our objectives are enhancing elderly safety, innovative fall detection, and preserving the independence of elderly. Our mission statement is to benefit from advancing radar technology to enhance the elderly safety by developing a fall detection system. These are some of our applications: home monitoring systems, hospital and rehabilitative settings, assistive living facilities, fall risk assessment, emergency response systems. This is our literature review. These are the main 5 papers that we focused for our literature review. The first paper, Millimeter Wave Radar Based Elderly Fall Detection Fed by One-Dimensional Point Cloud and Doppler by Chennaram Kittapunya et al. This system uses mmWave FMCW radar, LSTM network, data pre-processing, data filtering, and so on. This achieved an accuracy of 99.5%. The drawback is that the sliding window of processing may cause overlapping. The second paper, Human Activity Recognition Based on Frequency Modulated Continuous Wave and DenseNet by Wenshuo Jiang et al. Here the FMCW is used and the machine learning technique used is DenseNet, which is a convolutional neural network. It has achieved a 95% accuracy for human activity recognition. The disadvantage is that no other convolutional neural network can be used for non-image recognition. Our third paper, Fall Detection Using 4D mmWave Radar and a Hybrid Variational RNN Autoencoder by Feng Jin et al. This uses silicon germanium bi-CMOS technology with heterojunction bipolar transistors. Here, it includes the 3 dimensions and time, hence it is 4D mmWave radar, and it has achieved 98% detection rate out of 50 falls with minimum false rates. But it is difficult to conduct experiment in complex living environments. Our fourth paper, IoT Ready Millimeter Wave Radar Sensor by V.A. Ahmed et al. It uses multi-purpose 60 to 120 GHz TRX chips, a 79 GHz chip for automotive application, binary phase shift keying and modulators. It has a range resolution of 6 cm and ranging precision of 100 micrometer at 1 meter range. The drawbacks are signal interference or environmental effects. The fifth paper, Exploring Human Pose Estimation and the Usage of Synthetic Data for Elderly Fall Detection in Real-World Surveillance by Sardar Jurve et al. The technology used are post estimation methods such as alpha post, DC post, open post, open PIFPA, and so on. It does a quantitative assessment of post estimation model, but it suffer under various conditions like occlusion, dim light, and many produce false positives or miss key points in certain scenarios.
So in any project, finding out the target user is an important task. So in our project, primary target users are the elderly individuals. Secondary target users are the caretakers of family members. Or tertiary target users are the healthcare individuals or the neighbors. So from the feedback or opinions, the needs of the target users, we finalize the target needs as privacy, contactless, real-time monitoring, weight, and alert and ease of use. So these customer needs should be constructed with the factors that we consider when implementing a system, that is accuracy, sensitivity, response time, cost, fault alarm, maintenance, material, range, frequency. So from these need metrics, we finalize these our target specifications. Our accuracy is ideal values 95, marginal values 98, and so on. And our range of our system is about 6 to 10 meter. Frequency is about 60 to 64 gigahertz.
So this is the block diagram of data processing chain of TI mmWave radar. This is what is happening inside the IWR6843 board. So the transmitter antenna sends a FMCW signal and the receiving antenna receives the reflected signal. The transmitted signal and received signal are mixed and it is sent through a low pass filter and it is converted to an intermediate frequency signal. This intermediate frequency signal is converted to a digital signal for further processing. The further processing is done in a DSP processor and the range FFT and velocity FFT are calculated and the phase difference between the range and velocity is taken as the angle of arrival. The output of the mmWave radar sensor is a point cloud data which is sent to the PC via USB. So this is the basic block diagram of our system. So the output from mmWave radar sensor as point cloud and Doppler velocity is sent for data pre-processing. Data pre-processing include data filtering and sliding window method. In data filtering, we eliminate unwanted noise and remove static clutter. Sliding window is used because if we use batch windowing, there is a chance of missing some particular faults happening between two windows. So here we are using sliding window. Hence overlapping problems can be solved by setting a threshold value. So LSTM network is used for the classification purpose. The LSTM network has mainly 5 layers: the sequence input layer, LSTM layer, fully connected layer, softmax layer and classification output layer. The sequence input layer takes the input from the point cloud input. The LSTM layer is the core layer and it is used to control the flow of information. Fully connected layer is an additional layer particularly for classification purpose. This layer integrates the information from the LSTM network, and the softmax layer converts the values from fully connected layer to probabilities, and based on the probability the classification output layer decides whether it is a fall or a non-fall. So this is the structure of an LSTM network. The LSTM network mainly has the LSTM layer mainly has 3 gates: input gate, output gate and forget gate. Input gate decides which data should be stored in the system. The forget gate decides whether particular data should be kept or discarded, and the output gate decides which data should be exposed as output. The LSTM network has a cell state, and the forget gate functions according to the value of this in the cell state. Here the functions use the sigmoid function, hence all the gate function in the range of 0 to 1. Hence the output of an LSTM network will be in the range from 0 and 1. So this is the fault detection algorithm we used. So the algorithm is based on FMCW principle. These are the main equations that we use. The first equation is the sinusoidal FMCW signal. Then we have the equation of instantaneous frequencies of received signal that are obtained at the time of mixing between transmitted signal Xc of t and received signal Xr of t. The resulting IF signal of n point targets are given below. Then we have the equation of our intermediate frequency signal, and also we have the range FFT, Doppler FFT and the angle of arrival.
So these are the hardware and the software requirements. In the hardware part, we use an IWR6843 ISK ODS board. And in case of mounting device, we use a tripod for this, and in the computer we use a PC of Windows 7 or 10, and we also use a micro USB cable. And for the power supply, we transfer the power supply from the PC or the computer. And this is the IWR6843 ISK ODS board. And the software used are TI mmWave SDK version 3.6 and mmWave Industrial Toolbox. That's also the version, latest version is 3.6. Unified version 8.6.
So
And for hardware.
Now we will see the hardware setup. Initially, radars were placed 1 meter high on a wall, but this setup yielded suboptimal resolution. Moving the radar higher and tilting it improved coverage by 50% when targets were within 1 meter, addressing the signal spread issues. To improve coverage, the radar was tilted at 55 degrees towards the ground, broadening the wave signal's coverage area across the human body before reflection. So these are the different views when the radar is placed at a height of 1 meter and when it is placed at a height of 2.6 meter with a 55-degree tilt. So this is the output data structure. This is how the data is obtained at the output of the wave radar sensor. The data has a header, the detected object, range profile, noise profile, 2D FFT, the range Doppler heat map and status info. This is our use case diagram. Our use case diagram mainly have 4 users: the engineer, elder, caregiver and maintenance and installation way.
So these are the results and discussion. These are the results of our IWR 6843, and this graph shows the distance of the target object from the sensor, then the Doppler and the range and the relative power. And this is the demo of the setup done for the data visualization. This is the 3D scatter plot and the range profile of the object detected. These figures shows the human presence detection and fall detection. And the fall detection with a single person. Here is a video. And here is the fall detection. And fall detection with the 2 persons at the same time in a room. And fall detection with 3 occupants at the same time in a room.
So these are the
results and
discussion of our project. Our system was able to accurately detect the falls, and it also enabled long range detection, and the number of false alarms were reduced, and the system is privacy focused. So this is the design for our casing. These are
the bill of our materials. Mainly the radar sensor we used almost 7,500 rupees, and almost the casing the material we used is PLA filament, and the amount is rupees 1,000. And the connector we used for USB cable is also rupees 450, and the stand tripod we used for hanging the radar sensor is rupees 250, and the grand total is 10,300. And the achievements part of our conference paper has been published in the IEEE Expert. And these are the references taken for the purpose of our project.